Welcome to our detailed exploration of XN-based inter-NG-RAN handover in 5G networks. In this video, we focus specifically on handover scenarios where the user plane function, or UPF, is not reallocated. Let's first understand the key components involved in an XN-based handover. As a user equipment moves from one GMB to another, the XN interface allows for direct communication between the base stations, facilitating a smooth handover process. In this comprehensive video, we will cover several important aspects of XN-based handover without UPF reallocation. We'll explain what XN-based handover is and the specific scenarios where it's used. You'll learn the detailed step-by-step procedure, understand the benefits of avoiding UPF reallocation, and discover the practical implications for both the network and end users. Understanding this handover mechanism is crucial for network engineers and anyone working with 5G technology, as it represents an essential process for ensuring seamless mobility in modern networks. What is handover in 5G networks? Handover is a critical process in 5G networks that maintains continuous connectivity as users move between cells. It transfers data transmission from one base station to another without interrupting the user's connection. As a user moves from one cell to another, the network must transition the connection without dropping data or disrupting service. During handover, the network coordinates a smooth transition by transferring the session context, quality of service parameters, and buffered data between base stations. Handover is essential for enabling seamless mobility in 5G networks, preventing service interruption, and maintaining connection quality as users move. The XN interface is a direct connection between two G-node Bs, or GNBs, within the same next-generation radio access network. This interface provides a direct connection for signaling and data transfer between neighboring base stations. The purpose of the XN interface is to enable direct communication between base stations without involving the core network. To understand the importance of the XN interface, let's compare it with N2-based handovers, which involve the core network. N2-based handovers require communication through the core network, creating a longer path with additional signaling overhead. In contrast, XN-based handovers establish a direct path between the source and target GNBs, resulting in faster handovers with reduced latency. The XN interface provides several key benefits for 5G networks, especially during handover procedures. These include faster handover procedures, reduced signaling overhead, lower latency during transitions, and improved service continuity for users on the move. The XN interface specifications are defined in 3GPP technical specifications TS38420 through TS38.425. Inter-NG-RAN handover refers to a specific type of handover in 5G networks. It occurs when a user equipment, such as a smartphone, moves from a cell served by one GMB to a cell served by another GMB. Let's visualize this process with a network diagram. Here we have two GMBs, a source GMB, where the UE is initially connected, and a target GMB to which the UE will move. The key characteristic of inter-NG-RAN handover is that both the source and target GMBs are part of the same next-generation radio access network, or NG-RAN. During this type of handover, the UE physically moves from the coverage area of the source GNB to the coverage area of the target GNB, requiring a transfer of the connection. The critical requirement that makes this an inter-NG-RAN handover is that both GNBs must be part of the same next-generation radio access network. This allows them to communicate directly over the XN interface. This configuration enables the two GNBs to communicate directly with each other, facilitating a more efficient handover process compared to handovers between different radio access networks. The user plane function, or UPF, is a critical component of the 5G core network architecture. As part of the 5G core network, the UPF serves as the gateway between the radio access network and external data networks. The UPF is responsible for several key functions in the network. It handles packet routing and forwarding, enforces quality of service policies, measures and reports on network traffic, performs packet inspection, and supports lawful interception when required. The UPF serves as an anchor point for user data sessions. It maintains session continuity when users move between cells, routes data to and from external networks, and acts as the terminal point for protocol data unit sessions. In XM-based handovers without UPF reallocation, the UPF continues to serve as the anchor point for the user's session, which reduces signaling overhead and maintains the same data path through the core network. Let's examine what no UPF reallocation means in an XN-based handover. Initially, the UE is connected to the source GNB, which routes data through the user plane function, or UPF. When the UE needs to be handed over to a target GNB, the XN interface allows direct communication between the two base stations. During handover, the UE's connection transfers from the source GNB to the target GNB. The critical aspect of no UPF reallocation is that the user plane function remains the same throughout the handover process. By maintaining the same UPF, the network avoids switching the data path to a new user plane function. This approach reduces latency during handover and simplifies the overall signaling procedures. In this scenario, the Access and Mobility Management function simply instructs the network to switch the downlink data path toward the target GNB while maintaining the same user plane function throughout the process. In an XN-based handover, the Session Management function, or SMF, makes a critical decision, whether to keep the existing user plane function or reallocate to a new one. There are three key reasons why the SMF would choose not to reallocate the UPF. First, when the target GNB is geographically close to the source GNB, maintaining the same UPF provides optimal performance for both base stations. Second, maintaining the existing UPF connection reduces signaling overhead in the network. Each UPF reallocation would require additional signaling messages through the core network. Third, the UE's service requirements may not necessitate a UPF change. If the current UPF can adequately support the user's connectivity needs, there's no reason to switch. By keeping the existing UPF when these conditions are met, the 5G network can provide a more efficient handover experience with reduced latency and signaling overhead. Step 1 of the handover process involves measurement reports. In this step, the user equipment continuously monitors signal strength from neighboring cells. The UE collects various signal parameters, including reference signal received power, signal quality, beam measurements, and timing information. As the UE moves through the network, it continuously scans and measures signals from all detectable neighboring cells. This is a 4-step process: scanning for neighboring cells, measuring signal parameters, filtering the data, and reporting to the serving GNB. The UE then compiles this information into measurement reports that are sent to the source GNB. These measurement reports are the foundation for the handover decision, providing essential data about network conditions that will determine if and when a handover is necessary. The quality and timeliness of these reports directly impact the efficiency of the handover process. In Step 3 of the XN handover procedure, the source GNB sends a handover request message to the target GNB. This message is transmitted via the XN interface, which provides direct communication between the two GNBs. The handover request message carries several critical pieces of information about the user equipment. Two particularly important components are the security information and QoS requirements. The security information includes encryption and integrity protection keys to maintain secure communications during and after handover. QoS requirements ensure that the target GNB can provide the same service quality for the UE's ongoing sessions. This entire exchange occurs using the XN Application Protocol, or XnAP, as defined in Technical Specification 38.423. Once the target GNB receives this request, it will evaluate whether it can support the UE's connection with the required service quality. Step 4 of the XN-based handover process is admission control. After receiving the handover request, the target GNB must determine if it can accommodate the incoming connection. During admission control, the target GNB evaluates whether it has sufficient resources to support the UE's connection with the required quality of service. First, the target GNB assesses available radio resources. This includes checking physical resource blocks, bandwidth availability, cell load, and interference conditions. Next, the target GMB verifies if it can meet the UE's QoS requirements. This involves analyzing parameters like the 5G QoS identifier, bit rates, delay requirements, and acceptable packet error rates. The target GNB also checks its signaling capacity to ensure it can handle the additional control plane traffic associated with the new connection. Based on these assessments, the target GNB makes a critical decision, either accept or reject the handover request. If the target GMB accepts the handover request, it will prepare radio resources for the UE and proceed to the next step, Handover Request Acknowledge. If rejected, the source GMB may attempt handover to a different target GMB. Step 5. Handover Request Acknowledge. After receiving the handover request, the target GNB must decide whether to accept the handover based on its current resource availability. If the target GMB has sufficient resources and accepts the handover, it sends back a Handover Request Acknowledge message to the source GMB. This acknowledgement message contains crucial information, most importantly the radio resource configuration that the UE will need to connect to the target cell. This radio resource configuration is essential for the UE to establish a connection with the target GNB. Without these parameters, the UE would not know how to access the target cell, and the handover would fail. In Step 6 of the XnAP-based handover process, the source GMB sends a handover command message to the user equipment. This command contains crucial information that the UE needs to successfully connect to the target cell. It includes radio resource configuration for the target cell, security parameters, mobility control information, and timing advance details. Upon receiving this command, the UE will detach from the source cell, apply the new configuration parameters, and begin synchronizing with the target cell. Following the command, the UE begins the process of detaching from the source cell. This is a critical moment in the handover procedure. With the configuration parameters received in the handover command, the UE now begins to establish a connection with the target cell. To summarize, the handover command is sent via RRC signaling and contains the target cell configuration. This command initiates the actual cell change for the UE and represents a critical timing point for minimizing service disruption during handover. In Step 8 of the XN handover process, the UE performs 3 key actions to switch its connection from the source cell to the target cell. First, the UE detaches from the source cell, terminating its radio connection with the source GNB. The UE then begins moving toward the target cell. Next, the UE synchronizes with the target cell. This involves acquiring the target cell ID, aligning timing references, and decoding essential system information. Finally, the UE establishes a new radio connection with the target GNB. This involves completing the random access procedure, sending RRC Reconfiguration complete messages, and establishing radio bearers. At this point, the UE is fully connected to the target GNB and can continue its communication session without any perceptible interruption to the user. An important technical note: during this phase, the handover execution occurs entirely at the radio level, while the core network remains unaware of the change until the path switch request in Step 10. In Step 9 of the XN-based handover procedure, the UE completes the handover process by sending a handover complete message to the target GNB. After successfully synchronizing with the target cell, the UE moves from the source GNB's coverage area fully into the target GNB's coverage area. The UE sends a handover complete message to confirm that it has successfully completed the handover procedure. This message includes essential information, such as cell ID and signal measurements. Once the target GNB receives the handover complete message, the UE is considered fully connected to the target cell. The connection is now established for uplink and downlink data transmission. The handover complete message is a critical step that confirms the UE has successfully synchronized with the target cell and established uplink connectivity. It marks the end of the radio handover phase and triggers the next steps in the process. With the handover complete, the network will now proceed to update the data path to ensure proper routing of data to the target GMB. Step 10 of the XN handover procedure involves the path switch request, which is sent after the UE successfully connects to the target GMB. Before the path switch, data flows from the UPF through the AMF to the source GNB. After the UE has successfully accessed the target cell and sent a handover complete message, the target GNB must request an update to the data path. The target GNB sends a path switch request message to the AMF to update the downlink data path. This is crucial for directing traffic correctly. The path switch request contains important information including the UE identity, security context, target cell ID, and PDU session information with QoS flow details. When the AMF processes this request, it updates the data path to direct traffic to the target GMB instead of the source GMB, while maintaining the same UPF. This step is critical as it ensures data flows to the correct GNB, maintains session continuity, and completes the handover process while keeping the same UPF. The path switch request is followed by a path switch request acknowledge from the AMF to confirm the data path update. Step 11 in the XN handover process is the path switch request acknowledge. In the previous step, the target GNB sent a path switch request to the AMF to update the downlink data path. The AMF responds with a path switch request acknowledge message, confirming that it has updated the UE's location information and data path. This message confirms that the network has successfully switched the data path from the source GNB to the target GNB. The path switch request acknowledge message contains several important elements, including UE context confirmation, updated location information, tunnel endpoints, and QoS parameters. With this acknowledgement, the network now officially recognizes the UE's new location at the target GNB, and the data continues to flow from the same UPF. This completes the 11th step in the XN-based handover without UPF reallocation process. In the final step of the XN-based handover process, resources allocated to the UE need to be released. At this point, the source GMB still has resources allocated to the UE, including radio resources, buffered data, and UE context information. After the handover is complete and the path switch has been acknowledged, the target GNB sends a UE context release message to the source GNB. This message triggers the source GNB to release all resources that were allocated to the UE, making them available for other users. The resources released include RRC connections, radio and transport bearers, packet scheduling allocations, buffered data in the protocol stack, and UE context information. Proper resource release ensures efficient resource utilization, increases network capacity, and reduces the risk of resource leakage, which could cause network inefficiencies. With this final step completed, the XN-based handover process without UPF reallocation is now finished, and communication continues seamlessly through the target GMB. One of the key benefits of XN-based handover without UPF reallocation is reduced latency. In traditional handovers with UPF reallocation, the process involves transferring the connection to a new UPF. As the UE moves to a cell served by the target GMB, a new UPF must be allocated and a new data path established. This UPF reallocation process requires additional signaling between network elements and establishment of new data paths, resulting in longer handover times. In contrast, XN-based handover without UPF reallocation maintains the same UPF throughout the handover process. When the UE moves to a cell served by the target GNB, the handover occurs directly via the XN interface between the GNBs. Since the same UPF continues to serve the connection, there's no need to establish new sessions or reconfigure core network elements, resulting in significantly reduced handover times. There are several technical reasons why avoiding UPF reallocation reduces latency. No need to establish new sessions at a different UPF. The existing data path is preserved, with only the endpoint changing. There are fewer signaling messages between network elements, and data forwarding can continue uninterrupted. For end users, this reduced latency translates to tangible benefits: uninterrupted video streaming during movement, seamless gaming experiences while traveling, and reliable connections for critical applications. XN-based handovers without UPF reallocation significantly reduce the number of signaling messages compared to handovers that require UPF reallocation. When UPF reallocation is needed, the procedure requires approximately 20 or more signaling messages, including complex session transfers between UPFs. In contrast, handovers without UPF reallocation need only about 12 signaling messages, eliminating the need for UPF reconfiguration steps. Network congestion is a significant concern in mobile networks, especially during high traffic periods. Traditional handovers with UPF reallocation generate a high volume of signaling messages, contributing to network congestion. By eliminating UPF reallocation, we can reduce signaling by approximately 40%, significantly decreasing network congestion. This reduction in signaling provides several key benefits: reduced core network load, less processing overhead, lower bandwidth consumption, and decreased probability of congestion. The XM-based inter-NG-RAN handover without UPF reallocation provides a significant benefit, a simplified process compared to alternatives. In this simplified approach, the handover takes place directly between the source and target GMBs over the XN interface, while maintaining the connection to the existing UPF. This simplified process provides several important benefits compared to handovers that require UPF reallocation. The simplified process reduces handover time by eliminating the need to establish new UPF sessions and set up new data paths. This leads to faster handovers and a more efficient network overall. By avoiding the complexity of UPF reallocation, the network can handle handovers more efficiently, resulting in better resource utilization and a more responsive user experience. Now let's examine the practical implications of XN-based handover without UPF reallocation for both networks and users. The implications can be categorized into two main areas: network benefits and user experience improvements. For networks, the elimination of UPF reallocation results in reduced signaling load on the core network. Network management becomes simpler as fewer components need to be reconfigured during handover. This approach enables more efficient utilization of network resources, as no new UPF session needs to be established. For users, the benefits are equally significant. Handover processing happens faster without UPF reallocation. The time of service interruption during handover is minimized, leading to better continuity. This results in an improved quality of experience, especially for real-time applications like video calls or online gaming. In summary, the no UPF reallocation approach strikes an optimal balance between network efficiency and user experience, making it advantageous for both network operators and subscribers. Studies show that this approach can reduce network signaling by up to 35% and decrease handover latency by approximately 40%. Let's explore recovery options for XN-based handovers when problems occur. In our first scenario, we'll examine what happens when the existing UPF fails during handover. When the UPF experiences a failure, the Session Management Function, or SMF, detects this problem. The SMF then initiates reallocation to a new UPF, updating data paths to maintain service. In our second scenario, we'll examine what happens when the XN interface between GMBs fails. If the XN interface between the source and target GMBs fails, direct communication becomes impossible. The network then falls back to an N2-based handover procedure, routing signaling through the Access and Mobility Management Function, or AMF. Let's summarize the recovery strategies available when problems occur during XN-based handovers. In addition to UPF and XN interface failures, the network can also recover from radio link failures. If the UE loses connection with both GMBs, it will attempt to re-establish a radio link with any suitable cell. Future trends in 5G are transforming handover procedures to be more efficient, dynamic, and intelligent. AI-powered handover management uses machine learning to predict mobility patterns and make intelligent decisions that reduce handover failures. Dynamic UPF selection enables on-demand allocation based on user needs and network conditions, optimizing latency through strategic placement. Integration of UPF with RAN brings user plane functions closer to base stations, reducing the data path length and improving performance. Network slicing allows for customized handover policies per service type, with dedicated resources and optimized mobility management for each slice. Open RAN architectures support multi-vendor handover solutions with programmable interfaces for more flexible and innovative handover policies. These trends are converging to create an integrated, intelligent network that dynamically optimizes handover procedures based on real-time conditions and service requirements. The future of 5G handovers will be more intelligent, highly dynamic, service optimized, and with significantly reduced latency.